Here's the deal with binomial distributions. Binomial distributions are dealing with discrete data. You should know what discrete data is. Discrete data can be represented in a histogram. Continuous data is represented by one smooth continuous curve. Binomial distributions will behave normally. And if they behave normally, we can apply the normal curve to it and look at probabilities that way. So I'll show you kind of how we're going to break this up and how it's going to mirror that normal distribution. And then tomorrow we're going to actually get into that normal distribution. We're going to get back into the z-scores, which we covered a while ago. I said we'd come back to it. It all relates to probability. Today we're going to look at probability. Probability of events happening, special kind of distributions. And we've already looked at a couple in class. But I haven't formalized it in terms of a binomial. Tomorrow we're going to talk about geometric. Day after that's normal. So binomial distributions, you need to recognize what a binomial distribution is. That is first and foremost. As we go through this class, we're going to learn more and more statistics. A t-statistic, a chi-square statistic, a z-statistic, a binomial probability, a geometric probability. You're going to need to know what to do in what place. Okay? That's actually going to be the most important thing because the calculator buttons are going to take care of the calculations for you. But if you use the wrong thing because you don't recognize it correctly, then you're going to get that answer wrong. Does that make sense? All right. So binomial distributions, here's the behaviors of them. Don't write these down yet. Wait for the next page. First off, properties consists of a fixed number of observation called trials. Okay? Each trial has two mutually exclusive outcomes, success or failure. And the problem that we just did on the quiz, it was domestic or international, or we called it international or not international. Okay? And it said international was success. So there's two outcomes, mutually exclusive. You can't fly international and domestic at the same time. Okay? Outcomes of the trials are independent. You should see that word of independent. Hey, if we're doing an and situation here, we're going to be multiplying some probabilities together. You multiplied some probabilities together already on that quiz today. Probably that each trial results in success is the same every time. That ties with the idea of independence. So what happens before, and think of it, those three customers standing in line. Whether the first customer flies international or domestic is independent of the next person, is independent of the next person. And each one of those three people, the probability that that individual is going to fly is 40%. Does that make sense? Okay. Binomial around a variable defined as x. X is the number of times it happens. If you're going to look, we're going to make binomial distribution tables just like you guys made a table today. Right? So here's the easy way to remember the properties of binomial distributions. Yes, in this class you learned a custom BS, and now we're going to learn about pimps. All right. First P is going to stand for predetermined number of trials. In other words, the problem that you guys just looked at, we talk about the next three individuals. Okay? Guess what the I is going to stand for? No. Independence. It's going to start with the letter I, guys. Independent events. Independent events. Again, the first person is independent of the second person, is independent of the third person. M. Mutually exclusive events. Again, in the context of the previous problem, you either flew domestic or you didn't fly domestic. You can't fly both. And lastly, the probability ITY, stays the same for every event or trial. EVERY. In this case, I'm using trials and events as the same meaning here. That word means the same in the context. Okay? So that's kind of your checklist to determine if something's a binomial probability or you're going to apply the binomial distribution. If whatever's being described for you satisfies those conditions, then you're going to go this route. It's almost like a flow chart. Does that make sense? If this, then do this. If this, then do this. Okay? We okay with that? I just think it's easy to memorize that way instead of memorizing that list. That's what your textbook says. All right. Here's what we're going to look at. Mr. Wood makes 85% of all free throws attempted. Yeah, right. But we're going to pretend that that's true. Let's see, I wish. At one time I did shoot 85%, and now I can't really probably get close to 50%. Mr. Wood makes 85% of all free throw attempts. That means I played basketball all through elementary school, all through junior high, all through high school, and all through college. I've had millions and millions and millions of free throws, and I actually have to keep statistics on all of them. And I calculated all that. I got up the 85%. Okay? No. But that's what I'm talking about in terms of context here. This 85% stands for that theoretical probability. That's over time. I've actually done millions of attempts, and it's came out to be that. Okay? Does that make sense? All right. Now, that's 85% over time. I want to look at my next 12 free throws. Okay? That's now gone into the realm of binomial distribution. Okay? Let's make sure that we've satisfied all the conditions. Predetermined number of trials. How many trials are we talking about here? 12 basketball shots. Independent events. Let's see. Each time I shoot the free throw, whether I make or miss my previous one, does it affect the outcome of the next one? Does it affect the outcome of the next one? No. So they're independent events. Mutually exclusive. What happens this time? I either make it or I miss it. Okay, I can't make and miss at the same time. And that's the last one. Probability is the same every time. So every time I shoot it, I have an 85% chance of making it. So that satisfies those conditions of a binomial. Are we okay with that? Okay. This is the next formula. It's given to you on the stats formula sheet. It is a sexy beast of a formula. It's a mess. Let me show you what it means and how to determine and kind of translate it for you, okay? So, here's what we're going to do. If I make 85% over my lifetime, I now want to know what's the probability that I'm going to make exactly 8 out of my next 12. Do we understand the question? Okay. How do we come up with that probability? Now, here's the catch with binomials. Here I am. There's my little basketball. And I'm going to shoot 12 free throws. Agreed? So my first free throw, I have a, 85% chance of making it and a 15% chance of missing it. My second shot, an 85 and a 15. An 85 and a 15. And then I'm going to have my third shot. And my fourth shot. By the way, how big is that tree going to get on my fourth shot? How big is that tree going to get over here for my 12th shot? That's going to be a mess of a tree. Do you agree with that? And that's going to represent every single combination. Because remember, right now, if I look at this, these first two are me making the first two. Right? And these first two are me missing the first two. Right? But I know out of 12 shots, I can miss 2, make 2, miss 1, make 3 more, right? There's a lot of combinations of making and missing, and that would be me filtering all through that ugly tree diagram. Right? And I got to imagine that you guys don't really want to do that tree diagram with 12.
Sounds like fun.
it was ugly enough with the 3 guys on the international flight. Okay? So here's what we're going to do. We're going to look at what I want to have happen. Success in this case. What is success in this case? Making 8 out of 12. Okay? What's the probability of success? What's the probability? 85? Do we agree with that? Okay. So, if we're thinking in terms of that big, huge tree diagram that was a mess, do we agree somewhere in that tree diagram I've got to make 8 of them? So I'm going to have 0.85 happen how many times? Do we agree it needs to happen 8 times? So I'm just going to write that here. 0.85 8 times. Does that make sense? And not only do I have to have 0.85 happen 8 times, I also, since I'm shooting 12, if I make 0.85 8 times, that represents my makes. How often am I going to miss it? 4 times. So I have to have 4 misses. Well, Mr. Wood, isn't that just 0.85 times 0.85 times 0.85 times 0.85 times 0.8 times, and then times 0.15 times 0.15 times 0.15 times 0.15? That would represent the situation where I make my first 8 free throws and then miss my next 4. Isn't there a situation where I'd make the first 2, miss 2, make the next 6, miss 1, make 1, miss 1, make 1? That's me making 8 also, if I did my math correctly. Right? Isn't that another unique tracing there? And isn't there other unique tracings in there? In fact, how many unique tracings are there? It's a great question, Mr. Wood. A lot. Right? Well, we learned this thing perhaps in Algebra 2, perhaps in Pre-Calc, probably not much. But there's this button on your calculator you guys may have seen. It's called NCR.
No idea.
Okay? I guarantee you it's on your calculator. I'll show you where it's at in just a sec. Here's what's really nice about that NCR button and what it means in terms of statistics. RCR is Richard Childress Racing. No NASCAR fans in here?
No.
NCR. Here's what NCR does for you. It counts the number of unique tracings you're looking for. Okay? C stands for counting. Once again, it counts the number of unique tracings. In this problem, I have 12 free throws. I would like to count how many unique tracings there are of me making 8 free throws. Does that make sense? What's NCR? It stands for the number of tracings. Number of tracings. And what I mean by tracings is, I gave you an example of me making 8 and then missing 4. That's one unique tracing. Then there's an example of me making 4, missing 2, making 4, missing 2. There's also one where I make 6, miss 3, make 2, miss 1. Does that make sense? Okay. 12C8. And 12C8, again, makes me not have to fill out that whole ugly tree diagram. Here's how you do it. Shockingly, it's, we go 12. That's the number of shots I'm talking about. Go to math, probability, and you see the button right there, NCR. 12 NCR, and what are we going to put there? 8. So there's 495 unique tracings of me making 8 shots. Well, think about it. Make 1, miss 4, make the next 7. That's one unique tracing. Make 2, miss 4, that's the next unique tracing. Agreed? You should agree that there's a ton of them. So 495, I'm going to multiply that by me making, how many shots? 8. And then I'm going to multiply that by me missing, how many? 4 shots. Does that formula make sense? Because remember, before you did 3 times that number, I think today, there was 3 unique tracings for the, right? And a lot of you guys saw that from Pascal's triangle. Pascal's triangle just gives you combinations. It's the unique patterning with Pascal's triangle. But in order to get this number, you would have to take Pascal's triangle all the way down to the 12th row. And I don't know that you would want to do Pascal's triangle to the 12th row. So I would just use your calculator to do these. Pascal's triangle starts like this. Yeah, it starts out easy. Right? But that's what you guys just did. This was 0 combinations, 1 combinations, 2 combinations, and 3 combinations. There's only 1 unique tracing. There's only 1 unique tracing. On the outside, there's only going to be 1 way that I can miss all my shots. There's only going to be 1 way that I can make all my shots. And it's going to be 0.85 12 times, or it's going to be 0.15 12 times. It's going to be, if I make 85% of my shots, it's going to be very rare that I miss all 12. You guys should agree that that's a very rare probability. Yeah, press enter. And that's your probability. And notice that fits in with a line. 8 out of 12 might be a little low. By the way, how many should I make? About 85%. How could I find out what I'm expected to make in terms of expected value if I make 85% of 12? There's a big hint there. 85% of 12. 0.85 times 12, people, will be the expected value.
Are you sure?
Okay. Yeah, you said 12 after I said 85%. I was like, you killed me, small. All right.
You should make about 12. That's about 85%.
Yeah. Do we agree that probably is going to be 0.06828? So about 0.06828. Yep.
If there's like a 13 in front of the decimal, would you count that 0 or no?
A 13 in front of this
Like it's
decimal.
like 13.06828.
Oh dear Lord, you're never going to have a 13 then.
Forever?
It's a probability.
No, but like if one of the expected value and like.
No, then those are all. Then that 0 becomes a significant figure.
Okay.
If it's 13.06, that's 4 significant figures because you need to have that 0 in there. Yeah. On this, though, we should never have a 13. In fact, big red flag if you get a probability that's greater than 1, people.
That's good.
First one makes 85% of his free throws. What's the probability makes 8 of the next 12? 13.2. Sounds good. No, but it's what my calculator said. I can't tell you how many times students have told me that. No, I did it right. It's what my calculator said. Well, that can't be right.
Calculator's only as smart as the person using it.
True story. Number 2.
That's what we call them.
Find the probability that Mr. Wood makes 11 or less. Do we agree that's 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8? Right? All the way up to 11, you got to add them all up. Do you guys want to do that? But there's got to be a better way. What is the better way to get to the answer of number 2 than going probability of 0 plus probability of 1 plus probability of 2 plus probability of 3? What? Why don't I just tell you? No, this is a class that I know how to do stuff, but I'd rather challenge you to think on how to do it because that's what you're going to do in the AP exam. We need the probability that x is less than or equal to 11. Do we agree with that?
Yes.
How many free throws did I attempt? 12. I don't know about you, but this idea should make sense.
1 minus
Probability that x is less than or equal to 11 plus the probability that x equals 12 will equal 1.
I got you.
Is that on the right-hand side a true statement?
Yes, 1 minus.
If I want the probability that x is less than or equal to 11, then it's just going to be 1 minus the probability that x equals 12. Almost as if Algebra 2 is all the math you need in this class. Algebra 2 is all the math you need. You need the ability to think in this class, which isn't exactly taught in Algebra 2. What do we got? Here's how I want you guys to set this up, by the way, to show you work. This will be 1 minus, and then show me the calculation. So it's going to be 12, choose 12. I'm just going to kind of put it like this, times 0.85. How many free throws am I making there? 12 times 0.15, 0. Yeah. There is only, again, if you're thinking kind of at the next level, 12C12, there's only one tracing that I make all 12. And by the way, what's anything to the 0 exponent? 1. So it's really just 25 to the 12th, and that should make sense. But I want to show you guys how that sexy beast of a formula right here, the probability that x equals k, parentheses n over k, pk, 1 minus p, n minus k. It's what I'm doing right now. Let me show you how that formula relates to this. When it says probability that x equals k, in this problem that I did up here, that was the probability that I make 8 out of 12. In other words, the probability that x equals 8. That is 12, choose 8. That's what it's saying. 12, choose 8. The probability of success, which was 0.85, that many times, which was 8 times. 1 minus 0.85, that's where I got my 0.15 from. And then it's going to be 12 minus 8, or 4. That's the formula. But I think with everything we've talked about, this makes sense. Or hopefully it should, where it's coming from. That's what that formula is saying.
Wait, so e to the x was 0.85 to 8?
That's 0.85 to the 8, yeah. That's the probability right there. These things are probabilities, so that's 0.85 and that's 0.15. And again, it's kind of nice to see if you look at it in terms of C. You go, this is success 8 times, 12 minus 8 is your failure. And again, 8, 4 have to add to the 12. It's just kind of all puts together. Here you go. That's your setup. That's how you show your work. Watch this. Again, I want to look at just this first problem. Is everybody okay with the formula, how it works, and where the numbers fit? Because again, that's how you have to show the work. Yeah. This is a binomial distribution. This?
Yeah.
This represents the probability that I make 8 free throws out of my next 12.
Okay.
All right. Calculator. We got 0.06828, correct? Everybody recognize that number? That was me making 8 out of 12. I want to show you, take your step into a brave new world right now. Press second bars. That gets you to distributions. As I told you, we're going to talk about a lot of distributions in this class. At the very top, you see a normal probability distribution function. We're not talking about normal things. I told you we're going to talk about t-distributions in this class. That's there. This little x squared stands for chi-squared distribution. We're going to talk about that later. You need to know when to use the right thing at the right place. I want you to go to the one that says binomial PDF. Okay? Bless you. Binomial PDF. That's the probability distribution function for binomials. Go up there. Scroll, hit up instead of down. Here's what I want you to put. N, comma, P, comma, X. N is the number of things we're doing. In this case, there's 12 free throws. Comma, P, that's my probability. What's the probability that I make a free throw? 0.85, comma, X. Okay? X is how many I want to make. How many I want to make? Close your parentheses. Hit enter. Oh, we now love our calculators.
That's an error.
I do love my calculator right now. I'm going
Okay. Now, I want everybody, notice that that number is exactly the same. You need to be able to show your work. We're short on time right now, so I need to show you this next button so you can get your homework done. Second distribution. Binomial. Now I want to go CDF. The difference between a PDF and a CDF. PDF is exactly that. I wanted 8. Cumulative is up to and including, so it's going to sum it for you. I want to show you a binomial CDF right now. We had 12, comma, 0.85, comma. I wanted 0 through 11, correct? Up to and including 11, hit 11 here, and it will sum it up for you.
I love my calculator.
Okay? Binomial PDF, binomial CDF are the buttons you need to use tonight. You also need to set up your work in the correct formula. Okay? I will post homework. It's also up on Blackboard. You guys are good to go.